Okay, hi everyone. This is going to be part 2 of chapter 18. This is um this is going to be a longer one. Last video we were just talking about how enolates were formed, but this video we're going to be talking about how they're going to react with other carbonyl compounds, right? So in this you know how enolates formed? We have an acidic carbon here with acidic hydrogen bonds, this alpha carbon of the carbonyl, right? And because of this acidity of the hydrogen, we can react it with a base. And what this base does is it's going to take the hydrogen and then form this enolate that we've been working with for our video last time, right? So here we have this enolate compound, and we know that this is in equilibrium with this if we do our resonance, which means that this carbon over here can be a nucleophile, right? So we know from 40A that carbons are better nucleophiles than oxygens, which means this resonance structure will be the most preferred. And we're actually going to be working with this a lot more than this one, right? So let's get into an example of what's called an aldol condensation, right? So here we have two carbonyl compounds, benzaldehyde and then this aldehyde as well. And we're subjecting it under basic conditions, right? So from what you know about carbonyl compounds, they do have this alpha carbon right over here, which has acidic hydrogens, right? So we're going to be focusing on that part of that chemical characteristic that they have. So if we look here on this carbon, it has 1, 2, 3, 4. It has 4 bonds already to the groups, which means there are no hydrogens attached to this alpha carbon, right? And this isn't an alpha carbon. But if we look over here, this has 1, 2, 3, 3 hydrogens connected to this alpha carbon. So what it's going to do is this this OH will take that H and then form our enolate, right? And then I'm just going to draw that first here with the resonance where we have this. And then we have our benzaldehyde, right? And then now we have a good nucleophile and we have a carbonyl compound, which we talked about in the previous episode, previous video, where this carbonyl compound has a delta positive on that carbon and a delta negative on that oxygen, right? So that means a strong base can come and attack this. So a strong base can come here and this will guide up. So that's what's going to happen here, where this is going to attack that. This goes up. Be careful about your carbons. Here we have 1 carbon, right? And here we have 1, 2, 3. Oh wait, this is a aldehyde, sorry. So here we have 1 and here we have 2, 3. So we're going to add 2 more carbon bonds to that. So let's see how that happens over here. Right? This has the O. This is 1, 2, 3, right? 1, 2, 3, and then this is a hydrogen, right? And then now this is negatively charged. Let's move this down so you all can see a little bit better. And then from up here, this OH took the hydrogen, so we have a water, which means that this can be protonated and we can form our alcohol, right? Oops. So it looks like that. But that means we're still going to be in acidic basic conditions, right, with this hydroxyl group. Do we still have more alpha carbons? We do. We have more alpha carbons right here, which means there's still H's that are going to be acidic, right? So we're going to do this process again, form this enolate, from that, we get this. Right? This compound. And then now this comes, this is where this is what sets apart the aldol condensation apart. This is what sets apart the aldol condensation from other reactions, right? And in other reactions, I'm going to make this a little bit bigger for you all to see. In other reactions, you've never really seen an OH leaving group, right? Let me also make this a little bit prettier. Sorry, I'm not an artist. Okay, so what happens is this oxygen with its lone pairs is going to form a double bond with the carbon. While that happens, this double bond over here comes and gets moved to the other carbon. And now you're going to have the removal of that alcohol. So it's going to look something like this. This O has that. This will got moved over here. And then we have our base catalyst, OH. Okay. So let's see why this is able to form, right? So here we have a conjugated system of pi electrons, right? We have a one carbon apart from it. So what this means is there's resonance here that can go up like that, right? So this is very stable, which is why this alcohol can leave with this formation. And this actually has a name for it, where this is the alpha carbon right here, right? So this is an alpha carbon, which makes this a beta carbon. So then it would be called an alpha beta unsaturated. And then this is a carbonyl, right? So it's an alpha beta unsaturated carbonyl. And these alpha beta unsaturated carbonyls are very, very stable because of this conjugation of pi electrons over here, right? Of this conjugation of pi electrons, this resonance here, and it can go up. Same thing with your idea of aromaticity, right? So when you have two carbonyl compounds under basic conditions, this is the type of reaction that can happen. And also, enolate formation can also occur under acidic conditions. But in this video, I'm going to just be focusing on basic conditions because it's more of what we see, right? Okay, so now let's go into crossed aldol condensation. So let's look at the differences between this reaction versus our top reaction over here, right? So let's look at this one first. When I'm looking at these types of questions, I'm always looking at where is the alpha carbon, right? So this is an alpha carbon over here, and then this is an alpha carbon over here. Do we have H's? We do. We have two H's that we can take, and we have three H's that we can take over here, right? So what's the difference between this reaction and the reaction above? In the reaction above, right, we only had one alpha carbon that we can take a hydrogen on, right? And this is what's making this reaction selective, right? We can't take any alpha, this alpha carbon doesn't have any hydrogen, so we can't take it from there. We can only take it from this compound here, which led to only one um, only one formation of a product, right? But with this reaction, this can actually go multiple ways because now, not only can you get this carbon and form an enolate with this compound, but you can also take it from this carbon and form an enolate with this compound, right? So you will have, you'll actually have a total of four products for this, where this one will be an enolate and attack this one will be an enolate and attack that, and since these two are in solution together, there is a possibility that they will react with each other. So it'll be like this, right? Plus, or this one, right? Because of this because the fact that they're in solution and there's a lot of alpha carbons that you can take, you're going to have a total of 4 different products for this, right? These are called self-aldol condensations, right? Because they're reacting it with itself. And here is called a cross-aldol condensation, which is what we've been looking at, right? So let's go through one of the reactions. Let's make this one an enolate over here, this aldehyde. So we have this alcohol. Going to take that H, make an enolate. Make sure you put the H's here and then negative charges. Right? And then now we can attack that carbonyl. And then let's see what we form over here. And then we added 2. Yeah, that looks right. We have 1, 2, 1, 2, 3. Oh, I missed 1. So we had 1, 2 carbons here, and we had 1, 2. So we added, so now we have a total of 4. So we have 1, 2, 3, 4. That looks better. And then now we have this negatively charged, right? And then we're going to take a water from it. Take this acidic hydrogen, form this. OH. And then now we still have our beta carbons, our alpha carbons, and we have hydrogens, right? This is our alpha carbon because it's right next to the carbonyl. We have hydrogens here, and then we can. Sorry, I figured out where my problem was because that looked really weird. So my problem was I had the hydroxyl on this carbon, but what happened was this carbon already had that carbon, right? So I didn't think about it. I was moving too fast, so that's my fault. So now we're back to the step, and then this is gonna come over here and get this. I think you guys caught on it. I don't know, but if so, I hope this doesn't confuse you. This O, this H, right? But we're still in acidic condition, basic conditions. And we still have more alpha hydrogens over here, alpha carbons with acidic hydrogens. Form that enolate that we already have again. Right here, here, and then this, OH. And then now comes that weird step of the aldol condensation, where we move this down. This goes over here, and then this OH leaves, right? So now we have something like this. I'll try to make it a little bit better. Over here, right? And then now it's an alpha beta conjugated system. So that's what happens in an aldol condensation. With this, there are going to be more products, like I previously said. It's going to be self-condensation and where this one will be our enolate now, right? So make sure you try those at home. Hopefully you're able to get it. It's very repetitive. You're making an enolate here. You're attacking that enolate to the carbonyl compound. There's this protonation where it takes the hydrogen, and then you still have more alpha carbons with acidic hydrogen. So you take it with your base again. And then this is the only weird step over here where you get rid of that OH group and you form this alpha beta unsaturated carbonyl. Okay. Now let's go into something a little more challenging. This is called intramolecular aldol condensation, right? As you can see here, this is a lot different um, from our regular problem that we had because now we have 2 carbonyls that are in the same molecule, right? This is why it's called intramolecular aldol condensation. So let's see. We can either take, there's a lot of alpha carbons over here, right? We have this alpha carbon, we have this alpha carbon, this one's alpha carbon, and then this one's an alpha carbon, right? But what happens if we take the alpha carbon from here? If we take the acidic hydrogen from this alpha carbon, our enolate is going to form with this carbon as being the nucleophile, right? And if this carbon is a nucleophile, you can see how this carbon is going to attack this carbonyl, right? Because it can't attack the carbonyl that it's sort of directed onto or connecting onto. It's going to form a 1, 2, 3. It's going to form a 3-membered ring, right? And that's not stable. You learned this in 40A where ring strains occur, and that's really not a stable compound if you form a 1, 2, 3-membered ring. But if you form a 1, 2, 3, 4, 5-membered ring, it's a lot better, right? We can either take it from this one or this one. It doesn't matter because they are symmetrical right down the middle. So I took it from this one because it's closer to that OH. So let's see what happens. Take that. This goes over here. This goes up top. And now we have this compound over here that I just drew for you all. This is missing a double bond here. Sorry. And then now if we do our resonance, this is a nucleophilic carbon, right? And then now it's not going to attack onto here because it can't do that. It can attack all the way up here and make that ring. So let's see, how do we make this ring? I think this is the hardest or like one of the most difficult patterns to see. So let's just number our carbons, right? This carbon is attacking, so we're going to call this 1, 2, 3, 4, and then this carbon over here is 5, where it's attacking, right? So let's just make a 5-membered ring first, right? And then let's number our 5-membered ring. We have 1, 2, 3, 4, 5, right? At the 1, we don't have anything at the 1. At the 2, we have a ketone, right? At the 3, we just have 2 hydrogens, nothing there. We have 2 hydrogens here. 4, there's 2 hydrogens. At the 5, we have a methyl going one way and then this carbonyl going the other, right? So let's draw our methyl here. And we have our carbonyl, which got attacked and became this negative, right? And then we have our water again, because that's what attacked. And then now, if that happens, we get OH, and then that methyl. So now we're still under acidic conditions. Which one is going to be our alpha carbon? Is it going to be this one, or is it going to be this one up top right here? If you did this reaction in your head and you're seeing a few steps forward, it's going to be this top carbon over here. Even though this is also an alpha carbon, this top carbon will make it possible for the elimination of this hydroxyl group, right? So if we do that, form this enolate again. Yo, my drawings are horrible. Oh my goodness. I'm so sorry, y'all. Like that, right? And then this is negatively charged. And then now this makes it possible where we bring this down here and we do the weird step of the aldol condensation. And then we make this compound, which is again, alpha, beta, unsaturated, right? So this is one of the most difficult ones to see because it's intramolecular and you're forming a ring, right? But if you can see how we made this product and if you followed along, it's really the same steps. You're deprotoning, making it an enolate, you're attacking a carbonyl, you're making that carbonyl an alcohol, and then you're taking another alpha carbon with acidic H's, another enolate, and then the removal of that OH group and making the alpha beta unsaturated carbonyl, right? So this isn't hard. It's just very repetitive and it's very visualization based, right? So now we're going to move on to Michael addition, which is going to be our second to last chapter, our second to last topic that we talk about. And then we have our Robinson annihilation, which is a really big one. Okay. So we formed this alpha beta unsaturated carbonyl, right? This is alpha, this is beta. And then I told you that this is very stable, right? And what happens here is there's this resonance where if this goes up here, then this goes here, right? And if that happens, we form a positive charge on this beta carbon, right? This beta carbon here has a positive charge because the resonance made it lose its double bond to this alpha carbon, right? Because of that, we have two nucleophilic sites that we can attack, right? We have this partial positive on the carbonyl, and we have a full positive on that beta carbon, right? So there is a naming system to this. So the naming system starts, 1 is at the oxygen, 2 is at the carbon containing that oxygen, 3, 4, right? And if we attach a nucleophile to this 2 position, right, because there is this partial positive on this carbon here containing that oxygen, right, carbonyls, it's called a 1-2 addition, right? Because it's a partial positive, only strong nucleophiles can attack. I'm talking about Grignards. I'm talking just those strong nucleophiles, right? But most likely, because of this fully positive charge over here, it's going to do a 1-4 addition, where if that happens, if it's a 1-4 addition, sorry, there should be this double bond here, and then this double bond here. This can happen with, and this is what we're gonna see, where we're gonna see this happen with our enolates, right? Because even though they're carbon nucleophiles, they're very hindered by the groups that they have, right? So we're gonna see this 1-4 addition, and this 1-4 addition is called a Michael addition, right? So let's see an example of a Michael addition. We have this. We have our 2 alkanes here, right? 1, 2, 3, 4. And then if you number it from the oxygen, we have 1, 2, 3, 4, right? And we have our carbonyl with acidic hydrogens, right? You've seen this before. That happens, form an enolate, right? And then negative over here. And if we react it with that, I said up above that enolates will prefer to add onto 1-4. So we're going to do that because of this positive charge over at this carbon because of the resonance, right? So it's going to add onto this. This bond will move over here, and then this will move up. Here comes the hard part of seeing it. We have 1 carbon here, 2, 3. So we're going to have 3 carbons. 1, 2, 3. So we have this H over here, and then O, right? And then at this, we have the oxygen here. And then this is negatively charged, right? So this reminds me of a keto-enol equilibrium, right? Because if this goes on and does the resonance here, we can have now this compound over here with this carbon being our nucleophile, right? And go back to what we talked about keto-enol equilibrium. Which one is, if you don't remember keto-enol equilibrium, this can either exist as that and or this. So this is in tautomerization with each other, right? And you can sort of see how that's going to form over here. We just, well, first we need a hydrogen on this oxygen, right? Which will make it an enol. Or we need a hydrogen to this carbon, which will make it a keto, right? From this, which one is more stable? If you said the keto one is more stable, this one, you are correct. The oxygen can hold this double bond better than this carbon would, holding on this to this double bond, right? So if that happens, and we can see that there is resonance here where this carbon is also negatively charged, the hydrogen will actually want to come over here and form a keto product rather than an enol, right? You can see what happens if this takes the H, it's going to become like this, which is an enol, right? But if this carbon takes the H over here, it's just going to become a ketone, right? Which is a lot more stable than an enol. So that's actually what's going to happen, because now, since these two are in resonance with one another, we have to draw our arrow, and then we can erase this part over here. And then we have a water compound over here, right? And that is going to deprotonate that carbon, form something like that. And then now we formed a keto compound that is more stable than an enol. And we just added carbon groups to it, right? So it's going to look like that. This is our final product with our base catalyst, right? I hope I didn't miss a carbon. Let's see. 1, 2, 3. 1, 2, 3. Yeah, I'm good. Okay. So this, again, this is Michael addition. We have this alpha beta unsaturated carbonyl compound, right? And then we have our aldehyde or carbonyl compound over here. This OH is going to come deprotonate this and form our enolate compound over here. Then it's going to add 1,4 to this alpha beta unsaturated carbonyl. When that happens, we have a chance to either form an enol or a ketone, keto or enol, right? And keto is going to be the one that's mostly preferred because of the oxygen handling this double bond better than this carbon, okay? And then we have this compound, which looks a little bit weird, but you know, it is what it is, okay? And now we're gonna do something a little weird. We're gonna do the Robinson annihilation, which is our last reaction of this chapter. This is going to go a little fast because there's a lot to cover here, but I will go more in depth during Saturday, I think, which will when we'll have our study session this time, right? So here we have a uh, a cyclic ketone, right? And then we have a uh, alpha beta unsaturated carbonyl compound with a base, right? So again, there are a few ways to attack this problem. Since this is our alpha beta unsaturated carbonyl, we're not going to take it from here because this is actually where we're going to be doing our 1,4 addition, right? So we're going to take it from the cyclic ketone. We can either take it from the top or the bottom because these are both alpha carbons. I'm going to take it at the top, right? I'll show the steps. And I think now at this point, you're all tired of me drawing the resonance structure. So I will just draw the this carbon as a nucleophile over here, right? But again, remember that there is the resonance there, right? Okay, so now we have a nucleophilic carbon, and we have a 1,4 unsaturated carbonyl compound, right? We're going to attack it at the 4 position. There's that resonance, and then there's that one. Okay, so this is gonna look a bit weird. Let's see what we made. We have 1, 2, 3, 4 carbons. Okay, so we're gonna do that. 1, 2, 3, 4. Okay, that looks good. It's at that position. And then at the 1, it went down. Oops, this should be a single bond. It should be like that, right? And then now this is a negative over here. And then we have our water group, which will deprotonate that over. Oh, actually, no. Oh, yeah, we still have our water. And then now, this is the keto-enol equilibrium, right? And let me show that a little bit better. We have our ketone here, and then we have this, right? If we draw the resonance for this, and then we have a water. And then now, like I said, ketones are better at handling charges than the enol. So it's gonna come attack that. And then now we form this compound. Okay? But that's not all, because now we're still in acidic conditions over here, right? Because now we're still in acidic conditions, we have to choose which one is going to be our alpha carbon. Will it be this one, this one, this one, or this one, right? We have a lot of alpha carbons to choose from. So I'm going to choose, let's see, we're going to form a ring, right? Because we're going to attack it over here, or we're going to attack it over here. So I'm going to choose this one over here, because if I choose this one, the nucleophile will be on this carbon. And if this carbon attacks this carbon, it's going to form a 1, 2, 3, 4, 5, 6, 6-membered ring, right? Which is very, very stable compared to this carbon, where it's going to form a 1, 2, 3, 4, 4-carbon ring, which is not stable at all, right? So let's form our enolate from this. Right? And then this is, I'm just gonna go back to that enol compound again. Again, that there is the resonance there, but I'm just trying to make it quick for time's sake. So now we have that. And then let's attack this carbon over here with the carbonyl. And then now let's number our carbons. 1, 2, 3, 4, 5, 6, right? Let's do that here. So let's number it here. We have 1, 2, 3, 4, 5, 6, right? So now at the 6th position, there's going to be that oxygen there. At the 2, there's going to be a carbonyl over here, right? And then this is going to be negatively charged. And then we have our water again, which is going to come deprotonate that. This is, so I'll break it down. I'll break down the steps over here. So this right here is a Michael addition. This over here is a keto enol equilibrium, right? This one over here is intramolecular aldol condensation, which we learned up above, right? And then now this step will be advancement of the intramolecular aldol condensation, where this is going to take that hydrogen. Right? And then now we're still in acidic conditions, so it's going to be repetitive again. And then we have our alpha carbon over here, which we can take. And then we can do our magic step once we draw this compound. Right? And then now our magic step would be making this ketone, doing that, and then kicking out that group, which will make this compound over here, right? So again, let's go through this quickly. We first made an enolate, and then we did a Michael addition to this alpha beta unsaturated carbonyl, right? With this came our keto enol equilibrium, where we believed and we argued that it's better for the carbon to take the hydrogen because a ketone handles the double bond better than the alkene, right? If that happens, we have now a ketone over here, but we're still in basic conditions and we have a lot of alpha carbons to work with. You can also take it from this alpha carbon and attack this ketone. It doesn't matter. It's going to give you the same, um, it's going to give you the same uh, um, product, right? So what we did is we took it from this carbon over here, because if we took it from this carbon, this will be a nucleophile and it will form a 1, 2, 3, 4, 5, 6 membered ring, which is what we did here. This is intramolecular aldol condensation, right? Remember from our last step, 2 ketones. And then once that happens, we reprotonated this negatively charged oxygen with the water that just came out. And we're still in basic conditions. We still have our alpha carbon with acidic hydrogens. So this base is going to come attack that. It's going to come over here and form this this enol again, enolate, right? And then our last step, which is the aldol condensation part, is where we got rid of this hydroxyl group and the formation of an alpha beta unsaturated carbonyl again, right? That is a lot to take in, but take a quick look at this. It's very repetitive. Every step in this, you know how to do already. It's just very repetitive and it's very weird, right? There's no new chemistry going on here. The only new chemistry is this Michael addition over here and this weird condensation process where you kick off a hydroxyl group. And the only reason why that can happen is the formation of this alpha beta unsaturated carbonyl. Okay. I hope this was able to help and I hope you all have a good day. I'll see you all on Saturday, hopefully. If so, okay, have a good one.